Hello everyone. In this video, we are going to learn about some of the basic terms of probability. Um, this is a very important concept in computational statistics. And the reason why it is very important is because at its heart, probability is our way of measuring uncertainty. Now think of this example. Right now it is 8 or 9 p.m. on a Saturday and I'm sipping something from this coffee cup. What are the chances that I have coffee in this cup? Well, it can be the case that the number is zero, which means it's impossible that I have coffee in this cup. Or it can be one, which means that you're absolutely certain that there's coffee in this cup. Or it can be some number in between. You can take a 50-50 chance, 25%, 75%, depending on different factors you plug in. Now, the reason why we care about all this is because probability forms the foundation for statistical inference. How we make educated guesses about the world based on limited data. That is why probability matters. It is also key to understanding randomness in the data, which is everywhere in our modern world, be it weather forecasting, medical studies, betting. Probability helps us make sense of that randomness. So let's get into some of the fundamental concepts of probability. First, we need to understand what we call the sample space represented by this cap omega symbol. So what this symbol represents is the set of all possible outcomes in our experiment or the random process. For example, if you're flipping a coin, our sample space has two potential outcomes, heads and tails. If we are rolling a six-sided die, our sample space has six outcomes, 1, 2, 3, 4, 5, and 6. Any event in any event is a subset of that sample space. It's a collection of outcomes we are interested in. So if rolling an even number is an event, then that will include the outcomes 2, 4, and 6. If rolling an odd number is an event, that will include outcomes 1, 3, and 5. The probability function that we denote as P of A, we write P of A. What we mean is the probability value that we assign to this event A. And this is where the math comes in. So let's briefly just try and understand what the axioms are. What we mean by axioms is a set of basic rules that probability must follow. First is the probability of any event must be non-negative, which means that you cannot have a negative number denoting P of A. It can, at the very least, be zero, which means that the event is impossible. Or it can be at the most one, which means that it is a certainty, but it cannot be negative or more than one. So it is bounded in both ends by 0 and 1. The probability of omega is 1, which means that the probability of the entire sample space is 1. In other words, something from this entire set of outcomes must happen at any given moment. Third, for disjoint events A and B, what we mean by disjoint events is that they cannot happen at the same time. Okay, so if I define A and B as two events, A and B are two events which we define as disjoints, then what will always happen is either A will occur or B, but never A and B together. And in that case, the probability that either of them occur, which is captured by A union B, this U over here stands for union, then the probability that either A or B will happen is the sum of their individual probabilities. But in a lot of cases, there can be scenarios where A and B can have an overlapping region. So you can have A or B or some chances that A and B happen together. In that case, for events like that, we have this expression A union B becomes the sum of A and B, and we subtract A intersection B. The reason why we do that is because, we subtract this probability to avoid over double counting. Okay, so if you have A and if you also add B, if you just add them together, you're counting the overlapping region twice. So you need to subtract the A intersection B once to make that correction. So these are the fundamental concepts that we will be working with. A lot of probability problems comes down to counting and figuring out how many ways something can happen. So let's talk about some powerful counting principles that will make our lives easier. First is the multiplication principle that says that if you can do task 1 in m possible ways and task 2 in n possible ways, then I need to figure out a way to. So, okay, sorry, I got a bit sidetracked. So if you can do task 1 in m possible ways and task 2 in n number of ways, then both tasks can be done in m times n ways. For example, if you have 3 shirts and 2 pairs of pants, and assuming that you don't care about fashion at all, you can just combine any of these shirts with any of these pants, then you can have 3 times 2, which is 6 different outfit combinations. Seems simple, but it's incredibly useful for more complex problems. Next, let's talk about permutation. A permutation is an arrangement where the order matters. So if you have n distinct objects and you want to arrange R among them in an order, then the formula is P n R, which is n factorial by n minus R factorial. In other words, if you have 10 students and you want to seat 5 of them in a particular order, then you can do it in P 10 5 possible ways. The exclamation mark is the factorial symbol, which, for example, 5 factorial means 5 times 4 times 3 times 2 times 1, which is 120. So if you have 10 runners in a race and we want to know how many ways we can have gold, silver, and bronze medalists, then it will be P10 3, which is 720 different possible outcomes. So not only we are selecting 3 out of those 10, but the ordering matters here as well. But what about scenarios where the order doesn't matter? That's what we call combinations. So when we talk about combinations, all we care about is selecting. If I have 5 objects and I want to select 3 of them, how many different ways I can make that selection? That's what combination captures. It is C n R, which is n factorial by R factorial times n minus R factorial. This is just the math expression. So in R, fortunately, we don't have to make these calculations by hand. We have this choose function for combinations where we plug in the value of n and the value of R, and it will spit out the all possible ways. Or if we want to take a longer route, we can use a factorial function and get the same result. So let's think about some very classic probability examples. I'm aware that there's quite a few of you who are enthusiasts in cards, so this is an example for you. So in a standard deck, we know that there are 52 cards with 4 suits, hearts, 4 suits, and each suit has 13 cards, right? So what is the probability of drawing an ace from a standard deck? Well, There are 4 aces in a deck out of 52. So the probability of drawing an ace is 4 out of 52, which is 1 by 13. The probability of drawing a face card, which is jack, queens, and kings, is 12 out of 52, which is 3 by 13. The probability of drawing a heart is 1 upon 4. Okay. Another example is die rolling. So there are 6 possible outcomes in the cap omega space. The probability of rolling a 6 is 1 upon 6. Probability of rolling an even number is 3 upon 6 because 3 out of those 6 outcomes are even. So you have 3 possible outcomes that are consistent with the event. You have 6 possible outcomes that are there in the total sample space. So 3 out of 6 makes it 1 by 2. So you have 50% chance of rolling an even number. What is the probability of rolling a number greater than 4? So the first thing is, so what are the outcomes that satisfy this condition? There are 2 outcomes that can satisfy this condition, 5 and 6. So that is 2. So 2 out of 6 makes it 1/3. So you have a 1/3 probability of rolling a number which is greater than 4. So this is the basics of probability. Something that we use a lot is, and this is important and also highly practical, is this idea of conditional probability. And this is where things get really, really interesting. So conditional probability answers questions like, given that an event has occurred, what is the probability that another event has also occurred? We write that as PA. This vertical slash stands for given B. So we read that as the probability of A given B. And the formula for that is PA intersection B divided by P of B, where P of B is positive. Okay. So let me give you an example. Suppose I'm choosing a student at random from a class where 40% students are taking statistics, 30% are taking calculus, and 15% are taking both. So if we know that a student is taking statistics, what is the probability that they're also taking calculus? So what we're interested here is P calculus given statistics, and that will be 0.15 divided by 0.4, which is 37.5%. Here's one more laid out example, and sometimes it is useful to think in terms of conditional probability because sometimes it can give you a result which is counterintuitive. So imagine you have a medical test for a disease that affects just 1% of the population. This means that only 1% in the population is known to have this condition. This test also has a sensitivity of 95%, meaning that if someone has the disease, then there's a 95% chance that the test will correctly show positive. It also has something that we call specificity, which in this case is 90%, which means that if somebody doesn't have the disease, then there's a 90% chance that the test will correctly show negative. So sensitivity captures the accuracy of the test in terms of having the condition. Specificity captures the accuracy of not having the condition. So now the question is, if somebody tests positive, what is the probability that the person actually has the disease? That's what, because, we use these tests to actually get information about whether the person has a condition or not. And that's where, a probability, conditional probability comes in handy. Let's define our events clearly. So D stands for person has the disease with a prevalence of 1%. T stands for the event that the person tests positive. Test sensitivity is what? It is the probability that a person with the disease will correctly have a positive result. So that is probability T given D, which is 0.95. 95% of the sick people test positive. Remember, the other 5% means that there's some chance that the test will will throw a negative result for an actually sick person. That chance is always there. The test specificity is PT complement, which means not giving, like showing a negative, like getting a negative result, given not having the disease, which in this case is 0.9. So 90% of the healthy people test negative. If a person tests positive, what is the probability that they actually have the disease? And what we are really interested here is the probability of D, which is the person having the disease, given T, which is the person testing positive. Now, we know the other way around. We know what is P of T given D, which is 0.95, but we want to calculate the other way. And there is this formula provided by Bayes, and so he used this expression. So probability of D given T is the probability that the person tests positive given has the disease times the probability that the person actually has the disease, whole divided by the probability of testing positive. Then we plug in the numbers and we get the probability to be approximately 0.88, which means that despite testing positive, there's only 8.8% chance of having the disease. Now, this might be surprising because even though the test is pretty accurate, which is 0.95, if someone tests positive, there's only an 8.8% chance that they actually have the disease. And the reason why it's counterintuitive is because we are not taking into account that the disease is rare, so a lot of these positive results are actually false positive. And this example shows why understanding conditional probability is critical, especially in fields like medicine. It helps us interpret test results correctly and avoid jumping the gun based on incomplete information. But it's a bit math heavy, so let me try and make it a little more intuitive. So when we have two events, we can have two scenarios. Either the events are independent, they're happening on their own ways, and one is not affecting the other in any way. That can be one possibility. And the other way is that in some cases one is driving the other. So there is some sort of dependence of one event on the other. If the events are independent, then or the other way around, we define events A and B to be independent if the probability of them occurring together, which is A intersection B, is just a product of their individual probabilities. So if PA intersection B equals PA times PB, then we can say that the events A and B are independent. It also means that P of A given B equals PA, which means that the conditional probability of A given B is just the same as a regular probability of A. In other words, B gives us no information about A. So this is the independent side. If not, then we have this Bayes theorem that says that probability of A given B is probability of B given A times P of A whole divided by P of B. Now this may look simple, but it's very powerful. It allows us to reverse conditional probabilities and kind of like come to a conclusion, like based on some information. It allows us to reverse engineer our information about some event. So in other words, if we know what is the probability of B given A, we can find out what is the probability of A given B as well. So think of P of A as our initial belief about the probability of A, which we call the prior probability. When we observe B, we update our belief to P of A given B, which is the posterior probability. Bayes' theorem is the foundation of Bayesian statistics, which is used extensively in machine learning, artificial intelligence, medicine, and many, many other fields. In our medical testing example, it helped us calculate the probability that someone has a disease given a positive test result by using information about the test accuracy and the disease prevalence. The law of total probability helps us calculate the probability of an event by breaking it down into mutually exclusive scenarios. So if I have events B1, B2 up to Bn, they form a partition of the sample space omega, which are mutually exclusive and exhaustive. Then for any event A, the probability is summation of Pa given Bi times P of Bi. Now this might look a bit intimidating, but the idea is simple. What we are doing is we are calculating the total probability of A by considering all the different ways A can happen across different scenarios. This is extremely useful because it allows us to break down complex probability problems into simpler parts, and it is often used with Bayes' theorem for updating probability based on new evidence. And in the medical example, using this law of total probability, we can update our probability that the person tests positive to 10.85%. So about 10.85% of the population will test positive, even though only 1% actually has the disease. Now let's talk about working with multiple events and set operations, which are essential for solving complex probability problems. First, we begin with union of multiple events. So you have A1, A2 up to AN. So there are several there are several events. So what this means is that the probability that at least one of them happens is, in a simple example, we sum the probability of them occurring individually, we subtract the pairwise overlap, and we add the probability that they occur together. And it gets a bit tricky, but because there's several layers of overcounting happening. So we need to avoid counting overlapping parts multiple times, and uh, this inclusion exclusion principle comes in. In other words, we add up all the individual probability, subtract the overlaps, and then add back the triple overlap to get the correct count. De Morgan's law helps us work with complements of unions and intersections. It's really useful for rephrasing probability problems in more manageable ways. The first law says that complement of a union equals the intersection of the individual complements. In everyday language, this means that if an outcome is not in either A or B, then it is neither in A nor in B. That's what the first law means. The second law states that the complement of an intersection equals union of the complement. So complement of the intersection equals union of the complements. In plain English, this means that if the outcome is not in both A and B, then it is neither it sorry, let me rephrase. So if an outcome is not in both A or B, then it is either not in A or not in B. And last is the conditional independence, where events A and B are conditionally independent given C, if knowing that both C and A occurred doesn't change the probability of B compared to just knowing C has occurred. So combinatorial probability brings together the counting principles we discussed earlier with probability concepts to solve interesting real-world problems. Let's take the first one, the birthday problem. So what is the probability that in a group of 23 people, at least two share a birthday? Most people guess this probability to be quite low, but actually the number is not that high. Instead of calculating this directly, it is often easier to find the probability that no one shares a birthday, that is, everyone has a different birthday, and then subtract from 1. So for the first person, any birthday is fine. For the second person, they need to avoid the first person's birthday. So they have 364 possibilities out of 365. For the third person, they need to avoid two birthdays. So that is 363 out of 365 and so on. And therefore, the probability of no shared birthdays is 365 times 364 times dot 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 up to this times 3 divided by 365 raised to the power n. And for n equals 23, this works out to be approximately 50%. So at least one shared birthday. So what this means is that in a group of just 23 people, there's already a slightly better than 50% chance that at least two share a birthday. And I think this is very interesting because you might think that birthdays, like two people having birthdays on the same day, is pretty rare, but it's not that rare if you think of it from a probability framework. Again, for the poker enthusiasts, what is the probability of a royal flush? There are four possible royal flushes that can happen, one for each suit, out of 52C5 combination. So that is 4 divided by 2.6 million, which is approximately 0.000154%. The probability of a full house is much higher, at least as compared to royal flush. It's approximately 0.14%. In probability, and more so in probability distribution, one term that people use often and often is expected value. The expected value, which is also the mean, is the average outcome we expect in the long run if we repeat an experiment many times. It is the theoretical average of a random phenomenon. So if I'm considering rolling a fair die, the expected value is 1 times 1 by 6 plus 2 times 1 by 6 plus up to 6 times 1 by 6, which is 3.5. But interestingly, 3.5 is weird because we can't actually roll a 3.5. This shows that the expected value doesn't need to be a possible outcome. It is just a theoretical average based on the values we are working with and the probability that we are dealing with. And the second is the law of large numbers that states that as we increase the number of trials, the average of our results will converge to the expected value. This is a very important theorem in probability theory because it connects theoretical probability with what we observe in the real world. So if I roll a die once, I might get a 6. If I roll it twice, I might get a 6 and a 3 for an average of 6 and 3 is 4.5. These small samples can vary a lot from the expected value of 3.5. But if I keep rolling the die over and over again, say for example 10,000 times, and then take the average, my expected value will be very close to 3.5. This principle is the reason casinos always make money in the long run. The games are designed with the expected values that favor the house, and the law of large number guarantees that with enough players, the actual results will be close to these expectations. Uh, there's a snapshot of the R codes. I will have a separate video where I will work through these, but this is just for convenience. The law of large numbers is also why statistics works, even if we don't want to acknowledge that it's working. This is the reason why we can use samples and make inferences about population. It is also why insurance companies can accurately predict their costs despite the uncertainty of individual claims. I think it's a beautiful result that connects math with the real world. So let's wrap this video up with some practical applications of probability. This gets applied in many different aspects. In risk assessment, insurance companies use probability to set premiums based on the likelihood of events like a car accident or home damage. Financial analysts use probability models to assess investment risks and portfolio diversification strategies. Healthcare providers use probability to evaluate treatment outcomes and make decisions about patient care. Quality control in manufacturing relies heavily on probability. By sampling products and understanding the probability of defects, companies can maintain quality standards without having to inspect every single item that they produce. Game theory uses this to analyze strategic decision making, whether it's in economics or politics or even sports. Understanding the probability of various outcomes helps people make optimal choices in competitive situations. Uh, Environmental scientists use probability to model natural disasters, like the likelihood of floods or earthquakes in specific regions, and that helps with urban planning and emergency preparedness. Public health officials rely on probability in epidemiology, for example, to understand how diseases spread and develop effective intervention strategies. Geneticists use probability to study inheritance pattern and gene frequencies in populations, which has applications from agriculture to medicine. Sports analysts use these methods to evaluate team players and develop strategies. And as you can see, there are so many different avenues where this gets used. So I hope this was useful. In a separate video, I will work through an R script and I'll show you how to use some of these concepts in R.